So now we're going to be looking for basically evidence whether there is a difference in two means from two different samples. And since we're doing a significance test, we're going to have a null hypothesis and an alternative hypothesis. So our null hypothesis is going to be that the difference between, oh, this isn't catching up, huh? The difference between the two means is some specified hypothesized value. Now, oftentimes we're just interested if there is a difference in two means, in which case the null hypothesis is just that mu1 minus mu2 is 0, or equivalently that mu1 equals mu2, right? And so I'll just remind us of the general idea. In a hypothesis test, we assume that this is true. Then we go out and we get two samples, one from population 1, one from population 2, and we take their difference. Now their difference is unlikely to actually be 0, right? And so there are two reasons that the difference in the samples that you got could be non-zero. One, it could be just because of sampling variability, meaning the true means are 0, they are the same, and we just happen to take two samples where they're not. Or if it's a very extreme difference, the other answer is that the true mean is not 0, meaning there is a difference. The null hypothesis is not true, and the alternative is true. And so what you calculate, what we call a p-value, is how likely is it that I get this sample if the null hypothesis is true? Okay, well, if it's reasonably likely that you get the sample that you got, then you don't have really enough evidence against the null hypothesis. If it's extremely unlikely that you get the sample that you got when the null hypothesis is true, then you have evidence against the null hypothesis and for the alternative, all right? So very small p-values are evidence for the alternative. P-values that aren't super, super small aren't evidence for the alternative. Well, what do I mean by super small? What's our threshold? What do we set as our cutoff to make that decision? It's alpha, it's the significance level. And that's generally about 0.05, although it can vary from problem to problem, right? Good. So hopefully the logic of significance tests is becoming a little bit more familiar now. Hey, guess what our conditions are? Random 10% and large counts. But now we have to check them for two samples, right? I'm sure you guys are, random and 10% have been the same no matter what confidence interval or test we've used. Large count, remember, for a mean is different than large count for a proportion. Large count for a mean could be three different things. One, if both populations are known to be normal, sample size doesn't matter and your large count is satisfied. Two, if you don't know about the shape of the populations, then if you know your sample sizes are both greater than or equal to 30, you're good. Large count is satisfied. Three, if neither of those is true, what do? Graph them. In this case, you would make parallel box plots, meaning box plots of both samples. Make some statement that you don't see any evidence of skew or strong skew or outliers, and then move forward. Same thing that we did in the last lesson, except now we're doing it for two populations because we're sampling from two populations, okay? All right. So let's see. has the mean number of hours Americans work in a week changed? One of the questions on the general social survey asked the respondents how many hours they work each week. Responses from random samples of employed Americans were recorded from 1975 and 2014, and they're summarized here. So 1975, we had a sample size of 764. They said they worked a mean of 38.97 hours with a standard deviation of 13.13 hours. 2014, we had a sample size of 1501. And there was a mean of 41.91 hours and a standard deviation of 14.35 hours. All right. I'm going to work fully through this one. And we're going to check conditions on this one. And then I'm going to do a couple more examples where we just assume the conditions are met, because everybody is clear that you have to check conditions on paper. I've said that enough times, right? But I feel like that's just such a rote part of this. And I really think that the learning part comes with the making sure you can do the calculations, know which tests to select, and conclude correctly. The rest of this is kind of robotic. All right, so let's state the appropriate hypotheses. We'll define the parameter of interest. We'll check conditions, and then I'm going to add C, conduct/conclude the test. Okay. All right, so let's go with state. And our parameter of interest is, I'm going to go M. I'm going to abbreviate this, 14 minus 75, meaning the mean of 2014 minus the mean of 1975. So true mean difference in hours worked per week. And I'm just going to make a note, that's 2014 minus 1975, right? This is an interesting question, because I mean, my intuition, and I think probably every generation's intuition would be like, hell yeah, I work way more than they used to. They had it easy. But one thing I think we've done to, like, I don't know, trick ourselves is, as technology increases, you just tend to work more, because 1975, what did you have, a landline? So you went home and you were done with work. But 2021, you're at work constantly. You're constantly checking email. And I mean, you guys are too. You're at school constantly. You're always looking at your emails. I'm getting student emails to open up AP Classroom at midnight on Sundays. You know what I mean? Like, I'm getting admin emails constantly. You're always at work. So I don't know how you would account for that. I guess they mean like how many hours do you spend at work, but you work, I don't know. I work at home as well, right? Like, I'm grading at home. So, all right. What's our null hypothesis here? Yeah, that they're equal. Good. So the equivalent of that, just because in our calculator, oh, you know what? No, I think in our calculator, that's fine, that they're equal. Mu 14 equals mu 75. And then our alternative, let's just make sure in the context of this, were they indicating a direction of the alternative or just a difference? Just a difference. And I put that in my head. I was like, we work more, so it should be greater than. But it just says changed, right? So this is a two-sided test. So we're going to go mu 14 not equal to mu 75. We're going to do this at the 5% significance level. All right. Let's check our conditions, plan. All right, so random. Both samples are SRSs, simple random samples. Okay, so 10%. I'm going to say safe to assume the workforce of 1975 is greater than, and just multiply your sample by 10, so 764, 7,640, and in 2014 is greater than 15,010. So again, this just verifies that our sample is less than 10% of our population size. And that it's basically safe to use our standard error formula. That's a question that'll come up every once in a while in a multiple choice section. Why do we check the 10% condition? It verifies independence in our sample, and that specifically lets us use the standard error formula, okay? And then large counts, this one's nice, we don't have to graph it because both samples, so I'll just call this sample 14 equals 1501, which is definitely greater than 30, right? And then my sample size from 1975 equals 764, which is definitely greater than 30. So we're good to go. All right. So let's do and this is going to be a 2 sample. What kind of a test? If it's for a mean, is it a z-test or a t-test? It's a t. T-test for mu1 minus mu2. All right. We'll go ahead and conduct this in our calculators. Awesome. So we're at our main screen. We're going to go stat. We're going to go to tests. This is a test and not an interval. So generally in these inference questions, I said there's a hierarchy. Number 1, decide, are we talking about means or proportions? In this case, means. Number 2, is it 1 sample or 2 sample? In this case, 2. Number 3, are we doing a confidence interval or a significance test? In this case, okay, so what option are we going to choose here? 4, 2 samples t-test. All right, are we doing it from data, raw data, or statistics that are given to us? Good. And then the order is important here because it's going to do mu1 minus mu2. So x bar 1 has to be whatever you decided mu1 to be. In our case, that's 2014, right? Yeah. So our 2014 mean is 41.91. Our 2014 standard deviation is 13.13.
think you mixed that up.
I did?
That's 75.
Oh, I was looking up top. Thank you. The standard, what's the standard? Okay.
14.35.
Thank you, 14.35. And our sample size is 1501. Our 1975 mean was 38.97. Those lazy jerks. Not even a full 40 hours. And 13.13. And 764. For mean, we're always going to say no to pooled. And then this is going to be our alternative hypothesis, and we specifically want to know if they are not the same. All right. Before I do this, let's just remember, we are assuming that there is no difference in the mean hours worked. We went out and took a sample, and clearly in our sample there is some difference between the mean hours worked between the 2 years, right? Now we're going to say, okay, assuming the true mean is 0, how likely is it that we get a sample difference this large or larger? If it's super unlikely, then we have evidence that there is a true difference. If it's not that unlikely, then we could go, hey, it was probably just variability from sample to sample. What's your guys' intuition for this one? Do you think we're going to have evidence for the alternative that there is a true difference, or are we going to fail to have evidence? Okay. What do you think? This one's hard because they're not that far apart, right? One's basically 40, the other one's basically 42. But with that in mind, these are pretty large sample sizes, which is going to give our test a lot of power to detect if there's any difference, right? So this one's pretty hard for me. I think it could kind of go either way, but let's see. Sorry, that's a calculus graph that's on top of this. Yeah, so our sample was really large, and our p-value is basically almost 0. So our calculator is just rounding it to exactly 0. So we do have good evidence, right? So t equals t, write down your t critical value when you're doing this. 4.8808, and that's basically how many standard deviations away from the mean your sample is. It's way out there. Because 3 standard deviations for the mean is like 99%, right? So 4 is like way out in the tails. And so P is approximately 0. And so what's our conclusion? Who can give me the first sentence of the conclusion? Just the general. The alternative. So I'm going to say at alpha equals 0.05, we reject H null in favor of HA. Sentence 2, you're kind of going to restate this, but you're going to add context. So we either have convincing evidence or we don't. Who else can give me the second sentence with the context?
Have sufficient evidence to prove that there is a difference between the true means in 1975 and 2013.
Excellent. So I'm going to say we have convincing evidence that there is a difference in mean work time per week. And I'll just do in parentheses 2014 minus 1975. Awesome. So you can see how sample size really affects the power of a test, even though this is like to me, it seems like a pretty small difference, like 2 hours. Since our sample sizes were so large, our test was really powerful and really able to detect even a small difference. And our p-value came out to almost 0, so we're almost completely convinced.
I have a really quick question.
Go ahead.
You said there are like 3 things that you said we should look for when we're trying to decide if testing it a bunch of the year. So it was means or proportions, 1 or 2 sample, and then what was the last one?
And then there's 2 types of inference we do, right? Either a confidence interval or a significance test.
Okay.
All right, so that's walking through a full significance test, checking conditions, everything. In this case with summary statistics. And this is like easiest case scenario where our large counts is immediately satisfied and we don't have to graph things, right? I don't think that when you have to do it with raw data, it's really much more difficult. It's just you have to enter the data into your lists, right? List 1 and list 2. So I think we will do one of those where we don't check conditions. All right, this is everything we just did. All right, so here, let's do one with raw data. I do want to practice checking, in this case, the large counts condition, so I will have us just in our calculator practice graphing the parallel box plots, but I won't make us go through the whole thing. We're just going to run the test and then conclude. All right, so does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed that a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic blood pressure. For a subject after 12 weeks in millimeters of mercury, an increase appears as a negative number. Here is the data. All right. Do the data provide convincing evidence that the calcium supplement reduces blood pressure more than a placebo on average, like the ones in this study? Okay, I'm going to have to go back because I don't know how to read this data. So hold on. So the response is the decrease in systolic blood pressure, and an increase appears as a negative number. All right, so we got to parse this data a little bit. So I am going to write out our hypotheses. So let's do, our parameter of interest is going to be, let's do mu calcium supplement minus mu placebo. And that's going to be the true difference in, I guess, reduced blood pressure. And I'm just doing it in the order of calcium minus placebo, right? All right, so our null hypothesis is easy enough, right? That would be that there is no difference. So mu c equals mu p. Here's where we're going to have to work together to crunch this. So positive values are good, right? And negative values are bad, right? Because that means an increase. So then we would want to see if mu c is greater than mu p, because a more positive value means more reduction, right? Does that track for everybody? Okay. So our alternative is going to be that the mean is greater for the calcium supplement than for the placebo. And we'll do this at the 5% level. So alpha equals 0.05. All right, I'm not going to make us write out conditions, but in this case, this is an experiment, right? This is not a survey. So we're not sampling. But when you check the random condition, you would say this is a randomized experiment, meaning they randomly assigned individuals to either treatment or placebo, right? In an experiment, you don't have to check the 10% condition. There's not a population. You still have to check large counts. In this case, the samples are under 30, so we would need to graph them in parallel box plots. Now we have to enter these data into lists anyway. I won't make you draw out the box plots, but let's just make sure we all know how to do parallel box plots. So go ahead and enter the data into list 1 and list 2 in your calculator. So stat edit. And hold on, I'll move my calculator. So in list 1 we want calcium, and list 2 we want placebo. All right, everybody have their data? So again, for large counts, we don't know anything about the parent populations. Sample size is not greater than 30, so we would want to graph parallel box plots. So once we have our data in there, we're going to go into stat plot. So second y equals. I'm going to turn plot 1 on. I'm going to choose the box plot with the outliers on it. I'm going to put list 1. We're good. I'm going to go back into stat plot. I'm going to plot 2. We're also going to turn that one on. We're going to have plot 2 be again the box plot with the outliers. I'm going to change my X list to list 2. And we're good. Then I'm going to just do, oops. I'm going to do a zoom 9. Okay. So again, what you need to include is sketch those out, and you're going to draw an x-axis below. You're going to label it with, in this case, reduced blood pressure. And then you're going to give it a sense of scale, and you can do that by hitting trace. And I would just label the 5-number summary along the x-axis. So just go through and make little tick marks on each one of these sections, below each one of these sections, and just label those to give it some sense of scale. But neither one of those is extremely skewed. Neither one of them has outliers, so we're safe to proceed. Make sense? All right, let's run the test. We're going stat, we're going tests. Again, running down the hierarchy. This is for a mean. It's 2 sample, and it's a significance test. So it's the 4th option, 2 sample t-test. And in this case, we're doing it from raw data. You just want to make sure you have it ordered. Since we're doing calcium supplement minus placebo, we put the calcium data in list 1, we put the placebo in list 2, so I already have the correct order here. I just want to change my alternative to greater than in this case, right? Go ahead and draw it out. Whoa, right over my box plots. There you go. That's your stats tattoo you can get for college right there. So much statistics on one graph. Ooh, p-value. Very close to significant, right? But what's our conclusion there? Yeah, it's above our significance level. So we fail to reject the null hypothesis in favor of the alternative. We don't have convincing evidence of a difference in mean blood pressure, calcium minus placebo. Meaning we don't have any evidence that the calcium pill is more effective than a placebo. Blood pressure is weird that way because it involves so many variables, right? Like stress causes a raise in blood pressure. So if you think you're taking something that's supposed to calm you down, you probably will calm down and then your blood pressure will lower. Same with things like pain medication and stuff like that. I don't think Tylenol has ever done anything like that.
Melatonin.
No, I think that's all placebo. My wife
I agree.
takes that stuff. Like,
I do too, and I know it doesn't work, but it still works. Even though I know it doesn't work.
but I also don't get headaches really or anything like that.
Oh, nice.
I get, yeah, I know that's such a, but I get like super grumpy at around 5 o'clock, like I'm a child. And I can't, there's nothing I can do about it. I need a pill for that.
That sounds like you're drinking coffee all day so you don't have a headache and then when it wears off.
No, I think it's more like, I'm the one who makes dinner at my house. And that's when it's like, I'm making dinner. I know I'm going to have to clean up. And then we're going to have to do the whole ritual of getting the kids to bed. All right. So good. We've done, I think, examples of sort of most of what you're going to end up seeing here. I am going to make a note. So remember that whenever you're taking 2 samples, there is the possibility that it's not truly 2 samples and it's paired data that's really a 1 sample situation. So you just want to be on the lookout for that. All right, so here's an example that looks like it's 2 samples, but it is 1 sample. They took a photo of me and put it in here back when I had a goatee and would wear black shirts. It's like the most early 2000s look ever. Just kidding, that's not me, guys. All right, researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table displays the data on the subjects' depression scores. Higher scores mean more depression. So in this case, it looks like two samples, but it's not two samples. It's not two randomly selected samples. Actually, each piece of data is paired with another piece of data, right? Like this is the depression score with caffeine for subject 1 and the depression score without caffeine for subject 1. So these aren't random samples from two different groups. This is actually a single set of data, and what we want is to look at the difference between the corresponding data values and then just run a one sample test on that difference. Does that make sense? So in this case, just intuitively, do you think that there is a significant difference looking at their caffeine scores versus depression? That would be my intuition, right? So what you would do in your calculator is you would enter, I would probably do it in the order placebo minus caffeine. I don't know. I'm averse to negative numbers for some reason. You could do it in either direction. But then you would do list 3 is list 1 minus list 2, right? So let's try that real quick. I won't make us check any conditions. Let's enter placebo in list 1 and caffeine in list 2. All right, so we have 16, 23. Okay. So once you have that data here, really what we want to do is, this is paired data. It's not actually two samples of data. We do want to find the difference in scores, but the difference for the individuals, not the difference in the samples as a whole. So we're going to do list 3, highlight that, and we'll just make that list 1 minus list 2. So I'm doing placebo minus caffeine pill. And that's the difference in their depression scores, right? And we would then want to run a not two sample t-test, but what in this case? Just the t-test. That's, if it doesn't say two sample, it's one sample. So just a t-test. We do it from data, and what we'd assume our null hypothesis is then that the mean difference placebo minus caffeine and depression score, we would assume is 0, no difference, right? And we're looking for evidence that placebo minus caffeine, there's actually a higher depression rate, right? So it's greater than 0. So that's going to be greater than mu naught. In this case, I need to go back to my list, and I'm going to be running my test on which list? Good. And we all kind of conjectured that that seems pretty statistically significant. The placebo depression scores looked a lot higher. Let's see if we were right. Yeah. We got a p-value 0.0027. So we definitely have evidence that caffeine withdrawal causes higher rates of depression, right?
Couldn't there be an argument to be made though that like people who already drink a lot of coffee might have like more, like experience more depression than like Like, not because of the coffee, but I don't know.
So yeah, if they were running, they didn't really mention how they sampled in this case, but if you're running a good experiment, right, you're going out and you're hopefully getting a sample of people where there's variability between their caffeine intake so that you can kind of account for that. But yeah, absolutely. All right, folks, so we've pretty much covered